So in this video I want to look at integration as a limit, and I want to look at area under a curve. If you remember back at the beginning of the year when we first learned about derivatives, we learned that you have a secant line, which is the slope of this line between 2 points, and as that line, as the delta x, this change in x from here to here, decreased, the secant line moved closer and closer. These points became closer and closer so that this delta x approached 0. And it was a limit. The limit as delta x approaches 0. And when it did, once these 2 points became indistinguishable, you had a tangent line. And so that's how we approached the derivative back at the beginning of the year. So we realized that this limit process got us from the secant line to the tangent line, or from an average rate of change to an instantaneous rate of change. And then eventually we saw a shortcut and realized that we could find the derivative by multiplying the exponent times the coefficient and subtracting 1. Something, like y equals 3x squared. And we said, oh, the derivative is 6x by multiplying and subtracting 1. And that was just a shortcut. But the long story was this whole process and doing it out formally using the limit. So just as differentiation came from the limit process, so does integration. And so that's what I want to talk about a little bit here, and then what it represents. So what mathematicians wanted to figure out was the area underneath a curve. Because it was easy to figure out, it's easy to calculate the area underneath something that's rectangular. So if you had this as a linear function, you want to know the area underneath, you would just do length times width. But when you have a curve function, it was difficult to determine exactly what the area underneath that curve was. So the way that mathematicians approached it was they realized that they had rectangles that looked like this, that you could get a pretty close approximation to the area underneath this curve by taking length times width of this rectangle and then length times width of this rectangle and then adding them together, because this area underneath here would pretty much almost fill the entire area underneath the curve. So it was an approximation. So what they were doing, they were using something called sigma, which is a way of adding up a series of things like these rectangles, and they were multiplying the length times width, and we were using delta x again, so each of these being delta x, change in x, if each of these were the same width. And so using sigma and adding up, length times width of this rectangle plus length times width of this rectangle, and that's what sigma does for us. And then calling each of these rectangles, we'll call it I, being the different rectangle, and we say, so the sum of each rectangle from I equals 1 to n being the number of rectangles, in this case 1, 2, 3, 4. So this is kind of a long story. I'm trying to make it short here. So this, what they realized was the more rectangles you have, the better approximation you have, because if I could fit a rectangle between here and put twice as many rectangles, I'd have less space above them. So if I did 8 instead of 4, I'd have a better approximation of the area underneath this rectangle. And so from, in this case, you say I equals 1 to 8, and you'd be taking length times width. That's what this is. This is delta x, and then f of delta x. I just meaning the first one, the second one, the third one, the fourth one. And so this is just multiplying length times width of the first one plus length times width of the second one, and that's what this notation is doing for us. And you get a better and bright approximation. And so the more rectangles you have, the better the approximation. So as n approaches infinity, so this became a limit, the limit as n approaches infinity. And so again, this is a long process that we're not going to cover this year, but if you were working through this process, you would see that you'd get the area underneath the curve. And then, of course, after doing this long process for quite some time, they started to realize that the integration was the shortcut that got them to the area underneath the curve. So that's what integration is actually doing for us, is helping us find the area underneath the curve. And I want to do an example, a basic example that can show that. So let's go to this graph here. So I'm going to do it with a function that you don't need calculus for, just to show that it works. And then I'll do one where you do need calculus. So this is not a curve, this is a straight line. And you can see the function is y equals 2x plus 3, which is linear, starting at 3, going up 2 over 1, up 2 over 1, up 2 over 1. I want to look at it from the interval from 1 to 4. So from here to here. I want to know what's the area underneath this function between 1 and 4. So basically I'm talking about the area underneath it. So what is the area of all of this here? Again, I don't need calculus for this, but I want to show you that it works. So if you broke this into two separate shapes, you can see this is 1, 2, 3 by 5, so this is 15, right? It's a rectangle. And then this is 1, 2, 3 by 6, which is 18, and cut in half because it's not a full rectangle, so it'd be 9. And so the total area is 24. So the area underneath this function is easily calculated, and it's 24. So what we're saying is if we were to integrate this function, so if we would take the integral of 2x plus 3 from 1 to 4. Now this is called, what am I trying to say? Definite integration, as opposed to what we were doing for, so let me just write that. Definite integration. What we were doing previously was indefinite, meaning when you took the integral of a function, you got another function. In this case, because you're going to be plugging in actual numbers, when you take the definite integral, you're going to get an actual numerical value, which in this case will be 24. So, so we take the integral, and the way we write this is so we add an exponent here, and we divide. So it's going to be x squared. We're going to divide by 2, but we've already got a 2 here, so 2 divided by 2 will be 1 plus 3x. So I'm doing integration. And then we're plugging in the numbers 1 through 4. So the way this works is you plug in 4. This is supposed to call us from A to B. We plug in 4. 4 squared is 16. Plus 4 times 3 is 12. Minus, and we plug in 1 squared is 1. 1 times 3 is 3. And I end up with 16 plus 12 is 28. Minus 1 plus 3 is 4. And I get 24. And this process that I'm doing is called definite integration. So you take the integral, you plug in the 4, you plug in the 1, you subtract the two values, and you get 24, which is the area underneath the curve. So this function this function is used to find the area underneath the curve of this function. So what I also want to show you is this function right here that I just took the integral. I took the integral of this one, and I got this function, and I have this function graphed here because that is also a function. So it has a graph, and it's a quadratic function. So here it is, and I drew the graph of it. And so what this is saying, so the function I started with, we really could call this y prime. And when we take the integral, we go backwards, we end up with y, which is this function here. Right? So this is a second degree polynomial. So this function, when you plug in 1, you get 4. That's this point here, 1, 4. And when you plug in 4, you get 28. That's this point here, 4, 28. So this would be like a position function. That's what I was trying to think of. So at let's say, at time 1 hour, I'm 4 miles away. And then 4 hours later, or 3 hours later, I'm 28 miles away. How far did I travel? 28 minus 4 is 24. So the original function tells me the distance traveled, and then the derivative of that function, which is this function, if I want to know the area underneath this function, I go backwards to the original function. So there's a relationship between a function and its derivative, or the derivative of a function and its integral. So one of them will tell me the area underneath the other. So that's how you use definite integration. Let me just show you an example. Now this was an example of finding the area underneath the curve where we could have, where we did it without calculus. And then I showed you here what it would look like with calculus. But let me show you one that you needed calculus for. So here we go. I want to know what's the area underneath this curve from 0 to 2. So what I'm talking about is, let me do this in another color, the area underneath this curve. And again, the way it was originally discovered, it was they had rectangles underneath here, and then adding them all up. But that process became a lot of work, and eventually they realized, wait a minute, all we have to do is take the integral of this function from 0 to 2, and this is called a definite integral, and I should get the answer to this should be a number. So if I add to this, I will get 3, so x to the third. This becomes 2/3. Let me just, and minus, and then I add 1 to this exponent, so this would be, oops, this was x third. And then I divide by 3, x squared divided by 2 plus 2x from 0 to 2. Plugging in 0 is going to be easy because 0 is going to make all of this 0. So basically I'm just plugging in 2. So 2 to the third power is 8. 8 times 2 is 16 thirds. Minus 2 squared is 4 times 3 is 12 divided by 2 is 6. Plus 2 times 2 is 4. I could just put these as thirds so that everything has the same denominator. So I could say 16 thirds minus 3 sixes are 18 thirds, plus 3 times 4 is 12 thirds. 16 thirds minus 18 thirds is negative 2 thirds, plus 12 thirds is 10 thirds. So that's approximately 3.3, and that's the area underneath this curve, is approximately 3.3. So this is called definite integration, and it's used to find the area underneath the curve. Again, I know this took about almost 15 minutes to make this video, but I explained the process that took hundreds of years to figure out. Mathematicians were trying to figure out how the heck do you get an area underneath something that's curved like this, and so they used a limit process of finding the area of rectangles over and over and over and over until someone realized, wait a minute, if you could just, integrate this and go back to the original function, so this would be your original function. If you took the derivative of this, you'll end up back here. And so we use the original function to find the area underneath the curve of the derivative, working backwards. So integration and differentiation are related in the same way that multiplication and division are related. And one of them finds the area underneath the curve. The other helps you find the instantaneous rate of change. Area underneath the curve also represents total distance traveled, because as I showed you, when you go backwards to the original function, you're talking about the position function, and when you plug in those numbers, you find the total distance traveled, which also represents the area underneath the curve. So they're related. I think I've said enough about that. We'll do some examples of this in class. I hope that was a good explanation.